Alrighty, guys. Good morning. Welcome back to Calc 2, and congratulations on surviving the second exam. You've made it. You're here. You're past the test. It's not all over. So I hope that you're feeling some amount of relief having that in the past. I know that some of you still, of course, plan to take it this afternoon, and that's okay. Let me see. Yes, I have made several appointments in G25. Let me just check really quickly, Enrique. Oh, because it's at G25 instead of in the bowl, I don't get a confirmation email. So what I'll do after class today, Enrique, I'll give them a call and make sure. Remind me what time that was going to be, just so I can verify. 11. Okay, yeah, I'll give them a call right after class here today. And if they say the appointment isn't there, it should be. We made it right after class the other day. But because I don't have a verification email to say for sure, yes, they did, yes, I did, then I'll double check for you, but you'll be fine, buddy. Alrighty. So let's get into the document camera and we can get started in earnest. Today is a really big and really exciting day for us because we are introducing the object of perhaps the greatest importance in all of this class, and that's a power series. So one of the questions I get a lot as we wade through the quagmire of chapter 11 is, why on earth are we doing all of this? Why all of this convergence stuff? Why all of these sequences? Why all of these series? Why all of these tests? And the answer is power series. So this is MAC2312, section 004, which is Calc 2. And today is the 5th of November, 2021. Today, we're talking about power series. And we'll be talking about power series for a little while. The specific section we're digging into today is section 11.8. I'm going to introduce and define a bunch of terms, and we're going to use a bunch of notation. But the thing I want you to keep in mind the big idea, a power series is a long polynomial used to approximate a nice, just say a function near a point. You've actually seen these before. We didn't tell you that you were seeing them before, but you've seen them before. You remember in Calc 1, there's a section just after you cover related rates, or right around the time you cover related rates, on linear approximation, where you discuss this function called L of x, the linearization for x. And then you use that to approximate things like the square root of 0.95 or the cube root of 8.03. Those were actually power series. They were short versions of power series. But you will see today, or not today, but you will see when we get into the section on Taylor's formula, that those are a special case of these things. But this is what I would like you to keep in mind. So there's going to be a bunch of notation. There's going to be a bunch of terminology. And I don't want you to feel intimidated by that. And I think the best way to do this is to just keep in the back of your head that all of these things, as scary as they may look, are just big polynomials. And the reason we're constructing them is to approximate some function, as long as you stay near a special point called the center. Okay. It's the case with mathematics that we have to give a definition. So I will go ahead and define a power series for you. And then we'll start looking at some examples. Okay. So a power series is an expression of the form sigma n from 0 to infinity Cn times x minus a to the n. The Cn's here, these are just like your ANs from the regular series early in chapter 11. The symbol a here is just a constant, and x here is a variable, just like we've been using the symbol x to represent a variable for the rest of the semester. In fact, you could write f of x equals this thing if you wanted to, right? Because it is really a function of x. The first few terms of this expression, we plug in n equals 0. You get C0 times x minus a to the 0, which is just C0. And we add to that C1 times x minus a to the 1. And then we add to that C2 times x minus a squared. Then C3 times x minus a cubed. And of course, the series goes on and on forever. We write that with the dot dot dots. So these numbers, C0, C1, C2, C3, these are called the coefficients of the series. This sequence, Cn, is called the sequence of coefficients. Just like when you talk about polynomials, right? The numbers that multiply the x's are called coefficients. The number a here is called the center. Okay. So these are the animals we're going to be messing with. Just like with all the other series we've talked about, there's the question of convergence. So does this series converge or diverge? And we know that if the series converges, it could converge absolutely and could converge conditionally. What's different here is that there's a variable involved. It's not just some numbers adding up, right? Over here, these aren't just numbers, there are x's, there are powers of x's, hence the term power series. So the question, does this series converge or diverge, on its own doesn't have meaning. The question that's relevant here is, for what x values does this series converge? So maybe if I plug in x equals 0, does the series converge? If I plug in x equals 5, does the series converge? If I plug in x is coming from some interval, does the series converge? I'm going to define for you just 2 more little terms, and then we're going to look at some examples, and I'll show you how to answer those sort of questions. Before we do that, just looking at this, looking at the first few terms or looking at it in this form, can anybody tell me a number that I can plug in for x, which will guarantee that this series converges? Don't think about it too hard. Most x values you plug in here, this expression is going to be infinitely long, right? If I plug in x equals 5 or pi or 10, this thing is going to be an infinite series. But there's one x value I could plug in that makes it a very much finite series. One value that makes all these terms 0. What is that x value? There's a suggestion in chat of plugging in 0. It's not a bad idea. Not a bad idea, but then this would be negative a, this would be negative a squared, this would be negative a cubed. So what is there an x value that I could plug in that would make this 0? Think about polynomials. Let me write some of this down. You guys can think for just a second while we write some of these things down. So no, the series above may converge or diverge depending on the value of the variable x. If, for example, we plug in x equals, so 0 isn't what we're looking for here, right? 0 is a reasonable guess, and for some series that would be the thing I'm looking for. But I'll ask one more time, what x value could I plug in to make x minus a all squared, x minus a all cubed equal to 0? Not necessarily 1/2. I'll give you a hint. It's not, let's just, a, right? If I plug in a, then this is a minus a. Then this is a minus a all squared. This is a minus a all cubed. So if we plug in a for x, the series is finite. Only has one term. And hence must converge. In other words, when you plug in the center, right? So this number a is called the center of the series. If you plug in the center for x, then this x minus a to the n term is 0. All of these terms over here are 0. So you're guaranteed to get a finite value out, right? That finite value is just C0, this constant. In other words, a power series will always converge when you plug in for x, the center. And what we're going to see is that there's a special interval which is symmetric about that number. But before we do that, let me just look at a quick example here and make sure we're comfortable with the terminology. So let's say identify the coefficients Cn and center A of the power series. Let's use sigma n from 0 to infinity, -1 to the n over n plus 1 times x to the n. Let's do 2 of them. How about that? Let's call this one S. And let's look at also sigma n from 0 to infinity, x minus pi to the n over n factorial times pi to the n. I claim that these are both power series, that these both fit into this form. And right now, all we're trying to do is figure out, well, okay, if that fits into this form, what is this and what is this? What are the coefficients, Cn, and what is the center, A? I'll put a little divider here. All All right, let's look at the series S first. Can anybody tell me what the coefficients Cn are in this series? You can type in chat or speak out loud. Remember, you can hold spacebar to speak.
It's everything to the left of x to the n.
Mm-hmm. Yeah, everything to the left of x to the n are your coefficients, right? So Cn here is -1 to the n divided by n plus 1. Those are my coefficients. And then if we try to match up the x to the n piece with x minus a to the n, this is one that would be good for Perez. What is the center of this series, whose kind of power terms are just x to the n? What value of a are we talking about here? What value of a will make x minus a to the n the same as x to the n? Don't overthink it.
0.
Damn right. 0. Right? In other words, x minus 0 to the n. That's x to the n. So when you see a power series where the power terms are just x to the n, that is a series centered at 0. And you'll see a lot of those. So just remember, x to the n is the same as x minus 0 to the n. All right, let's look at the series T. This one's a little bit harder to spot. I think we've got some work to do here. Maybe it's worthwhile to try rewriting this in a way that looks a little bit more like this. So I'll still have my sigma n from 0 to infinity. The x minus pi to the n looks like this piece. So I'll pull that over here. And then what's left over here? What becomes of the n factorial and pi to the n? Well, they were downstairs here. So this would be 1 over n factorial pi to the n. So this time, let's start with the center. What is the center of the power series T? Here. Again, I promise no tricky business. Don't overthink it. Just match this up with this. Well, this is x minus pi to the n, and this is x minus a to the n. So if a is the center, here, the thing that's playing the role of a is pi. So my center is pi. Yeah, very good, Kylie. Thank you. And then the coefficients, the Cn, are everything else in the series. It's the 1 over n factorial times pi to the n. Okay. So spotting the center and coefficients of your power series, it's an important thing you need to know how to do. And understanding what the center of a power series is, or at least how to see it, will help you begin to understand what we're going to define in the next step here. So remember, we said if you plug in the center, the orange note here, if you plug in the center, all of these terms would be 0, which means the series only has this one term, which may or may not be 0, but it's definitely finite. So all power series converge if you plug in for x the value of the center. Okay. Down the road, we're going to want to, given a function, find a power series to represent that function. And eventually, we're going to want to integrate and differentiate those power series. For now, though, and in the homework set that's opening for you today related to power series, for now, the task is just to figure out the x values for which the power series will converge. In other words, what can I plug into this thing? So this is a theorem. Associated with each power series is a real number I'll call it capital R, and it's both real and greater than or equal to 0, such that the series will converge, the power series, absolutely for all x's satisfying absolute value of x minus a is strictly less than r. This number, capital R, is called the radius of convergence. And I'll explain to you why it's a radius, right? Where that term comes from. And I want to help you sort of visualize what all of these x values look like. Before I do that, I want to say these are not necessarily all of the x values for which the power series converges. There could be as many as 2 others. But the solution to this inequality is the bulk of the x values for which the series will converge. All right. Why do we call this a radius? Well, what does the solution to an inequality of this shape look like? Some of us have talked about this in office hours, back when you were solving a few of the problems from section 11.2. You ran into inequalities of this sort there. They can be unpacked as negative r is less than x minus a is less than positive r. If the absolute value of some shit is less than the number r, how is that possible? Well, it means either the stuff inside the absolute value is positive and smaller than r, or negative, but not more negative than negative r, right? That's how you have an absolute value be small. You have to confine it on the left and confine it on the right. So this absolute value inequality is equivalent to this compound inequality without absolute values. And this sort of unpacking rule we will be using later in this section and all the remaining sections in chapter 11. I want to understand the x values we're talking about here. So I'm going to get x alone in the middle by adding a everywhere. If I add a everywhere, this becomes a minus r is less than x is less than a plus r. So in other words, all of these x values are all of these x values. The x values from a minus r to a plus r, which on the number line looks like this. Here's the number a. And that's the thing that we call the center of the power series. You're about to see why it's called the center. If I walk to the left, r units, starting at a and walking to the left, r units gets me to a minus r. And starting at a and walking to the right by r units gets me to a plus r. And what you notice is that the solution to this inequality is all of the x values that are in here. So my series, if someone hands you a series and then also hands you this number r, you can be 100% confident that your series will converge absolutely for any x value plucked from this open interval. All right, and this is an open interval right now. So the power series will converge absolutely for any x value coming from the shaded interval. And there remains a question, what happens outside of this interval? Does the series necessarily diverge? And what happens at these particular numbers, a minus r and a plus r, the endpoints to this interval? I know the series converges in here. That's really all this theorem tells me. It turns out that at the endpoints, it could go either way. And we're going to need to check them individually. It also turns out that outside this interval, the series is guaranteed to diverge. Okay. Let's look at a quick example. There was one like this that you guys had in your homework way back in section 11.2. Let's find all the x values for which the series S equals sigma n from 0 to infinity. How about x minus 2 to the n over 3 to the n converges? So really quickly, this series is a power series. Sorry. This series is a power series, right? And this problem, you might have had something other than a 3 here. You might have had like an e up here or something else like that. But you've done this problem. We've done a few variations on this problem. Although we didn't say it, that series is a power series. So I'm going to append to this old problem, state the center radius of convergence. Okay. A few different ways to think about this series now. If I'm thinking of it as a power series, where I want to be able to see the coefficients and the center, here it is. So the center is the number 2. The coefficients Cn are just 1 over 3 to the n. But does anybody remember how you solved these problems when you saw them first back in 11.2? There's a magic word for this series. It starts with a G. Anybody recognize this as a special kind of series?
Geometric.
Hell yes. This is a geometric series. Not all power series are geometric, but some of them are. This is the same as x minus 2 over 3 all to the n. So this, in addition to being a power series, is geometric. So we don't need any fancy convergence tests or anything like that to figure out where this guy converges or for what x values this guy converges. We just use our theorem on geometric series, which says the absolute value of little r, the common ratio, is less than 1. And here, that common ratio is the absolute value of, the common ratio is x minus 2 over 3. So the absolute value of that being less than 1 is what we're looking for. Now the absolute value of x minus 2 over 3 is the same as the absolute value of x minus 2 over the absolute value of 3, which is 3. We can multiply both sides by 3. And now I have an inequality that looks an awful lot like this thing. So you could actually read off the radius of convergence now as 3. Or you could unpack this as -3 is less than x minus 2 is less than +3. And finally, adding 2 everywhere. Oh, sorry, this pen is dying. -3 plus 2 is -1. X minus 2 plus 2 is x. And 3 plus 2 is 5. So we know exactly when this series will converge. This series, which is this series, will converge precisely when x is between -1 and 5. So I'm going to draw my number line, and I'm going to put the center right here. The center we said is 2. -1 is over here, and 5 is the same distance over here. So my series will converge for any x values in here. And you see that this distance is the same. So the radius of convergence center we already found, right? We saw that right away. And the radius of convergence is r equals 3. So that's it. That's it. We found the x values for which this series converges. The x values for which this series converges are those between -1 and 5. We found the center, and we stated the radius of convergence. When we do this with more general power series, they're not necessarily going to be geometric, right? This could be a more complicated thing. The coefficients might not just be some number to the n. And in those cases, we'll need to use other convergence tests, namely the root and ratio tests will be your buddies here. But the procedure after that is very similar. After you run the ratio test, you'll get an inequality, something like this, which you'll then need to solve and unpack to find this interval. Now, because the series here is geometric, there's no question about what happens when you plug in x equals 5 or x equals -1. You know that this series converges only for those values that keep the common ratio strictly less than 1. And when you plug in x equals 5, this common ratio here, 5 minus 2 over 3, this 3 over 3 is 1. That's a divergent series. When you plug in -1, this common ratio here is -1 minus 2 over 3. That's -3 over 3. That's also divergent. And you know if you take anything from outside this interval, the series will definitely diverge because those would have common ratios strictly larger than 1. I want to take a second and just pause here. Any questions on what we did with this example? Okay. A quick word about why we use the term radius. The one-dimensional analog of a circle, or the one-dimensional analog of a disk, I should say. So if you take a disk and you flatten it, is an interval symmetric about the center. In other words, they say to teach mathematics, you must tell the truth, tell nothing but the truth, but for the love of God, don't tell the whole truth. Here's maybe a little bit more of the whole truth. If we were working in a slightly more grown-up class where everybody was super duper comfortable with complex numbers, we wouldn't have an interval of convergence like we have here. We would have a disk of convergence, and that disk would be centered at the center, and it would have the radius 3. So this series, sure, it converges if you plug in any real number x between -1 and 5. That's true. It would also converge if you plugged in any complex number that lived in this orange disk in the complex plane. And that's why we use the term radius, right? Really, this interval is the projection of this disk in the complex plane onto the real line. And if you go on to take a very good differential equations class or a class on complex variable theory, then you will see this. You will see that all of the stuff we say about power series in this class generalizes beautifully to complex numbers. In fact, it's the right way to do things. Of course, it's just a little bit too much for this class, but I wanted to show you why a radius. Well, because it really is the radius of a disk. Now, you can't have a disk on the real line. The real line is a line. It's a one-dimensional thing. But you can have a disk in the complex plane. And if you take that center and that radius and you create that disk in the complex plane, then any complex number from that disk is a number you could plug into the series and get a convergent series as a result. Okay. I used a term there that I need to define for you. And then we're going to look at one or two more examples very quickly. Last call for questions on this guy. This is as easy as finding these objects get, right? If you're very, very lucky, your series is geometric. So I want to make sure we're all super duper comfy. Any questions about these manipulations, or how we knew to start with this inequality, or how we knew the series is geometric, anything like that? Okay. So the term I used there, without having defined it yet, is interval of convergence. The interval of convergence for a power series is the set of all x values for which the power series converges. Right? It's all the stuff you can plug in and get a convergent series as a result. And it is a fact, I'm not even going to state it as a theorem, it is a fact that the interval of convergence and if you don't mind, I will abbreviate this as IOC because that's just a lot to write, for a power series sigma n from 0 or wherever to infinity Cn times x minus a to the n. So in other words, for a power series centered at A is always one of the following. Right, so you know your series will converge if you plug in the center. And you know that there's some distance that you can walk away from the center and stay in that interval of convergence. That's the radius of convergence. If you walk outside of that radius, guaranteed to diverge, guaranteed. If you stay inside that radius, guaranteed to converge and converge absolutely. At the boundary, the endpoints, it could go either way. And what this means is that there's 4 possibilities for your interval of convergence. It could be like that last example, the open interval from the center minus the radius of convergence to the center plus the radius of convergence. It could be the left closed, right open interval. It could be the left open, right closed interval. Or it could be the closed interval. But it will always be one of these, right? It's always, in other words, the interval of convergence is always symmetric about the center. And may or may not contain either endpoint. it is a consequence of our theorem on geometric series that if your power series happens to be geometric, then the interval of convergence is automatically open, because you know that if the common ratio is equal to 1 or equal to -1, a geometric series diverges, and those endpoints are precisely the numbers that make that common ratio -1 or +1. But for every other power series in the universe, any power series that is not a geometric series, you could end up in any of these cases. Maybe you converge when you plug in the left endpoint, that would be this, and diverge when you plug in the right endpoint. Or maybe you converge when you plug in both endpoints. Or maybe you diverge when you plug in both endpoints, even though the series isn't geometric. All of those are possible. But no matter what, these series are always symmetric about the center, right? Modulo the endpoints. The endpoints, maybe, maybe not. But the interval itself is always symmetric about the center. Okay. I want to look at one example where we're going to play with Desmos a little bit. And then I'm going to show you, let's see where we're at, 10, 16. Yeah, let's do this. All right. So example. We're just going to look at the partial sums for the power series S equals sigma n from 0 to infinity x to the n. And we will observe the interval of convergence and compare the partial sums to the value of the series. All right. So I claim that we can find the value of this series. It's something we know how to do. This is, again, geometric. Let's do that first, so I know what to compare to. And let's also cook up our interval of convergence. So S is, again, geometric with common ratio R equals X, right? This is just sigma X to the N. So the common ratio there is X. Thus, S converges if and only if the absolute value of R, which is the absolute value of X, is strictly less than 1. And same deal, this means that -1 is strictly less than X is strictly less than +1. So the IOC is the open interval from -1 to 1. Just for fun, what's the center of this series? When I think of this as a power series, what is the center? Let's say both of these things. What are the coefficients and what are the center? Don't overthink it. Remember what we said earlier? X to the n is the same as x minus what to the n? Good, 0. Yeah, the center is 0. Perfect. Okay. What are the coefficients? What sort of things are multiplying my x to the n's?
1.
1. Very good. All right. So this is a series centered at 0, whose sequence of coefficients is just the sequence 1, 1, 1, 1, 1. All right. And based on what we know about geometric series, we're able to say that this guy should converge for any x values coming from the open interval -1 to 1. What are my partial sums? Well, I'll start with s sub 0. That's the sum from 0 to 0 of x to the n, which is just 1. S sub 1, that's the sum out to 1, so that would be 1 plus x. S sub 2, it's the sum from n equals 0 to 2 of x to the n, that's 1 plus x squared. I'll continue over here. S sub 3 is 1 plus x squared plus x cubed. S sub 4 is 1 plus x squared plus x cubed plus x to the 4, and so on. So these are the things that I'm going to graph for you in Desmos. I will graph for you these first few partial sums and maybe some extras. And what is the value of the full series S? How do you find the sum of a geometric series? And we have here a geometric series. How do you find the sum of a geometric series? What's that recipe?
The starting term over 1 minus r.
Beautiful, yeah. This is the starting term divided by 1 minus the common ratio. The starting term here, right? Look at the first few partial sums. The starting term is definitely 1. And the common ratio is x. So the value of this series depends on x. That makes sense, right? It's got a variable x in there. The value of the series is 1 over 1 minus x. So if you were to plug in some number x to this series that comes from this interval, and you want to know what is the sum or value of that series, it's 1 over 1 minus whatever it is that you plugged in. This is a function. It has a graph. And so do all of these partial sums. So when I talk about a power series converging, we're not so much talking about a series of numbers. We're talking about all of these functions, these partial sums, having graphs that get closer and closer and closer to this graph. And the catch is that this will only happen on this interval. Outside of this interval, these partial sums will not get closer and closer to this. But within this interval, these partial sums will get closer and closer to this. So here we go, Desmos time. First few times I saw this, it blew my mind. I hope that it is similarly fun for you. So I'm going to begin by saying s equals 1 over 1 minus x. Right. I'm going to turn my camera off, get this stuff out of the way. Here it is. Now, I'm going to graph this with the restriction here from -1 to 1. So really the part that we're expecting to see our partial sums get closer and closer to is the blue part. The red stuff really not a factor here. All right. Let me play some color games here really quick. And then we're going to reveal these one at a time. Toss in a few more. Oh. Oh, I made this blue, didn't I? So I should do something else. Not orange. Oh, no, orange looks too much like red. How about purple? Okay. So pay attention to the purple. All right, we're not worried about the red. The purple is 1 over 1 minus x, restricted to the interval -1 to 1. The very first partial sum, the 0th partial sum, is the line y equals 1. Now this guy is not a good approximating function for the purple. He happens to agree with the purple when you plug in 0, but everywhere else he's really far from the purple. All he does is go through one point correctly, and then out away from that point, he does a terrible job of matching up with the purple function. But he does at least agree at 0 at the center. Here's 1 plus x. What does this look like to you? If I gave you this picture and asked you, what is the relationship between the blue and the purple, what would you say? Think Calc 1. What Calc 1 object is this blue thing when compared to the purple or red graph?
The tangent line?
Hell yes, it is. This blue thing is the tangent line to the purple thing. The first partial sum of a power series for a function is the tangent line to that function. In other words, it's the linearization or the linear approximation function from Calc 1. So what does this blue thing do? This first partial sum? Well, he matches up with the function at the center. They share that point. But also, he has the same slope as the purple at that point. And you notice that if you stay really close to 0, like if you stay right in here, the gap, the vertical gap between the purple and the blue is not too bad. It's the best straight line for matching up with the purple. And if you compare that to the next partial sum, now this blue, he does an even better job of sticking to the purple, right? Not only does he go through that same point, but the blue parabola goes through that point with the same first and second derivative. He sticks really close to the purple as long as you stay close to 0. This is what I mean when I say these are polynomials for approximating a function near a point. This is the best second-degree polynomial for approximating the purple function near the point 0, 1. This cubic, let's see. So there's the quadratic. This cubic does an even better job. Look, that vertical gap is getting smaller and smaller the more terms I use. In other words, the blue functions are like gluing themselves to the purple function. They're going to kind of wrap up around the purple function. Here's the next one. And the next one. And the next one. Oh, this one's purple too. So what's happening here is that these blue polynomials are approaching this purple function. Now, they only do that when you stick to the interval -1 to 1. Outside of the interval -1, 1, if I zoom out a little bit, you'll see the blue and the purple diverge, right? They go apart. 2 roads diverge in a wood, whatever, right? They're going apart. They're not sticking together. But if I stay on that interval, -1 to 1, where I've kind of dyed the red function purple, the blue functions stick to it closer and closer and closer, the more and more terms I use. Oh, sorry, we lost this guy. There's a few more. So within the interval -1 to 1, this guy does a pretty good job, but not as good a job as this guy. And he does a pretty good job, but not as good a job as this guy. And he does a pretty good job, but not as good a job as this guy. Now imagine that you wanted to find the area under the purple function from like here to here. Imagine you want to find this green area. And for whatever reason, integrating the purple function is really, really, really hard. Right? Maybe it's just, you just don't know how to do it. It doesn't look like integration by parts or trig sub. Sure, here it's easy, but you can imagine I changed the function to something else. It could be really hard. Finding the area under the blue function here, well, shit, that looks like the same area, doesn't it? And the blue function, it's a big polynomial, but it's a polynomial. So you know how to integrate it. It's not hard. This is why we love power series. You can find the area under the purple or the area under the blue. It's the same area, or at least the error is very, very, very small. And there are ways to make the error 0. You can find the area under the purple. This might be very hard to do. The integral might be very hard to set up. Or you can find the area under the blue. Same area. But the integral of the blue is guaranteed to be very easy because it is a polynomial. It's just a power rule integral. So I wanted to illustrate to you what it looks like for the partial sums of a power series to converge. That was really the point here. I'll show you one more quick example like this. Maybe next time, because we do need to talk about one other thing. If there's time, I'll show you one more set of graphs like that at the end. Okay. To find the radius and interval of convergence for a general power series, right? If it's not necessarily a geometric series, if the series is geometric, yay, life's easy, good. But in general, these things don't need to be geometric. To do that, we will use the ratio test or the root test. Both of which will output an inequality, and we will solve that inequality for the open interval of convergence. Yes, Prashant, the purple was the graph of the function to which the series converged. So when we used our formula, 1 over, or the starting term over 1 minus the common ratio, that gave us the purple graph. And then the blue graphs were the terms of the series. So the full series is the purple, and the partial sums were the blue. Okay. So to find the radius or interval of convergence for a general series, you're going to use the root or ratio test. And I'll snag an example here. Find the IOC and ROC, radius of convergence and interval of convergence for the series S equals, how about the one we did earlier, sigma n from 0 to infinity, -1 to the n over n plus 1 times x to the n. This is no longer a geometric series because you've got this n plus 1 downstairs. Nothing magical. I will use here the ratio test. Remember how the ratio test works. L is the limit, n goes to infinity, absolute value of an plus 1 over an. If this comes out to be smaller than 1, the series converges absolutely. If this is larger than 1, the series diverges. And if this is equal to 1, then we don't learn anything. Here, though, because the ANs are this whole thing, there's going to be some x's in the limit, and the limit is in the variable n, so this thing will be a function of x. So we're going to set that less than 1. Let's just see what happens. This is lim n to infinity, absolute value. Now what I'm going to do is I'm going to write down an plus 1 in here, and then I'll multiply by the reciprocal of an. Same thing we were doing last week. So an plus 1 is negative 1 to the n plus 1, x to the n plus 1, divided by n plus 1, which is n plus 2. So there's your an plus 1. And now I want to divide by an, so I'll multiply by his reciprocal. So that is n plus 1 divided by negative 1 to the n, x to the n. And in the same spirit we did leading up to exam 2, we're going to shuffle things around and put the like terms together. That gives me lim n to infinity, absolute value of negative 1 to the n plus 1 divided by negative 1 to the n, x to the n plus 1 divided by x to the n, and n plus 1 divided by n plus 2. Each of these can be worked with pretty easily. Negative 1 to the n plus 1 divided by negative 1 to the n, we've seen a million times, is just negative 1. So I have here limit n to infinity, absolute value of negative 1 times. The same rule we use to simplify this to this, we can use to simplify x to the n plus 1 over x to the n to plain old x. And then n plus 1 over n plus 2, not much to do there. That's just n plus 1 over n plus 2. But remember, absolute values, these things, they play nice with multiplication and with division. So I can think of this like this. And since n plus 1 over n plus 2 is positive, he will lose his absolute values. The absolute value of negative 1 is 1. The absolute value of x is just the absolute value of x. And be careful there. You don't want to strip x of its absolute values. There's no guarantee that x is positive. N plus 1 over n plus 2, though, as n goes to infinity, that definitely is positive. This is just n plus 1 over n plus 2 without absolute values. And this x here doesn't have any n's in it. He can come out in front of the limit if you want. So all we're really taking the limit of is n plus 1 over n plus 2. And this limit, you've seen a million like it, is 1, right? So this is the absolute value of x times 1, or just the absolute value of x. So L, the number from your ratio test, isn't really a number, it's the absolute value of x. It's a function of x. Thus, L is less than 1 if and only if the absolute value of x is less than 1, because L is the absolute value of x. And we can unpack. You get negative 1 is less than x is less than 1. So what's my radius of convergence? This series, we said it earlier, is centered at 0. and I know here's -1, here's +1. I know for sure if I stay inside here, my series will converge absolutely, because those are the x values that make the ratio test limit come out smaller than 1. So what is my radius of convergence? What is this distance? Same as this distance. What is the distance from 0 to 1? Yeah, it's 1. Thank you. Right? So the radius of convergence is r equals 1. But I still do not know my interval of convergence. I know it's one of the following. Open -1 to 1, left closed, right open, -1 to 1, left open, right closed, -1 to 1, or the fully closed interval -1 to 1. And it's on us to figure out which one of these, right? What is the topology of the interval of convergence? We don't know that yet. We know it's an interval centered at 0 with radius 1, which means it could be any of these. You'll find that most of these problems go this way, right? Pretty much all the power series you're asked to find the interval of convergence for will go this way. You find the radius of convergence, you get that by running the root or ratio test, solving the corresponding inequality. I strongly recommend sketching that interval with the center labeled so you can make sure that you know what the radius of convergence is. But it's also true that when you arrive at this step where you have your absolute value of x minus a is less than some number, that number will always be the radius of convergence. But again, I strongly recommend sketching it so you can verify that the geometry makes sense. What I need to do to decide between these four is to check the endpoints. If my power series diverges when you plug in -1, then I know my interval of convergence cannot contain -1. So, could not be this guy, could not be this guy. If my power series converges when you plug in +1, I know that my interval of convergence must contain the number +1. So it could not be this guy, could not be this guy. And that would mean it has to be this guy. So after you find your radius of convergence, and you know that you have this list of 4 possible intervals, you need to check the endpoints. I realize we're going to go just a few minutes over here. I'll ask you to be patient. Finish this example. It's important. We need to check the end points. We must do this. At x equals 1, my series becomes sigma n from 0 to infinity, -1 to the, -1 to the n divided by n plus 1 times 1 to the n. 1 to the n is just 1. So this is sigma n from 0 to infinity, -1 to the n over n plus 1. I think this exact series was on, certainly it was in one of our recent lectures, and something like this may have been on your last exam. Does this series converge or diverge? Don't be shy, even if you're not sure, you got a 50-50 chance here. Does this series, what do we think, converge or diverge? Very good. This is a convergent series. It's a conditionally convergent series. This converges by the alternating series test. Very good, guys. This is the alternating harmonic series. This is the one that converges to that nice value of the natural log of 2. At x equals -1, my series is sigma n from 0 to infinity, -1 to the n divided by n plus 1 times -1 to the n. And this is slightly different than the previous series. This is sigma n from 0 to infinity. -1 to the n times -1 to the n is -1 to the 2n divided by n plus 1. And since 2n is always even, -1 to the 2n is always just 1. So this is sigma n from 0 to infinity 1 over n plus 1, which is 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, and so on. Does this series, think about writing it out in this form, converge or diverge? The series 1 plus 1/2 plus 1/3 plus 1/4.
It diverges.
Very good. It's the harmonic series which diverges. We know diverges. In other words, I could rewrite this as sigma n from 1 to infinity 1 over n. Right? You could say it's a divergent p series. You'd have to rewrite it as a p series to say that. Or you could argue that it's the harmonic series, or you could use maybe a limit comparison. There's lots of ways to verify that this is a divergent series. The simplest and cleanest one is definitely just observing that it is the harmonic series. So when we plug in x equals 1, I get a convergent series, which means 1 must be in the IOC. And when we plug in x equals -1, we get a divergent series, which means x equals -1 is not in the IOC. Remember, the IOC, the interval of convergence, is all the x values for which the series converges. So if your series does converge when you plug in an x value, that number is in the IOC. If your series does not converge when you plug in an x value, that means that number is not in the IOC. So which one of these does contain 1 and does not contain -1? Well, if I do contain 1, then that's the bracket. Oh, sorry, 1 bracket. And if I do not contain -1, that's the parentheses. So this is my interval of convergence. It is the left open, right closed interval. And this is generally how these problems go. You will run the root or ratio test to get to this stage. There you will observe your radius of convergence. And then you will check the endpoints to determine which of the 4 possibilities you're actually dealing with. So this power series converges if you plug in any x value strictly larger than -1 and less than or equal to +1. That's how you find intervals of convergence. Next time, we'll do a few more examples like this. I will show you some series have an infinite interval of convergence. Some series have an interval of convergence that is completely closed. And from there, we're going to talk about how to find power series that represent a particular function. Augustine DM's a really good question. Why doesn't the ratio test detect this stuff, the endpoints? Well, if we come back here and look at the ratio test limit, If you plug in either 1 or -1 for x, then the ratio test limit is the absolute value of that number is 1. So the ratio test is inconclusive at the endpoints. I like that. I like that enough that we should make a note. Since L equals absolute value x from the ratio test, the ratio test is inconclusive at x equals plus or minus 1, because those make L equal to 1. Yeah, it's a good question. So the ratio test isn't sensitive enough to pick up what's going on at the endpoints. Remember when we introduced the ratio test, we said, really, this test is looking for like fast convergence. The ratio test is asking what is the most similar geometric series, and those converge quite quickly. And this is a great example because at the right endpoint where the series did converge, this convergence is weak. This is a conditionally convergent series, not an absolutely convergent series. So when the ratio test does pick up convergence, it picks up absolute convergence. So even if we were to say that the ratio test limit coming out to 1 isn't such an unpleasant thing, remember that the ratio test, when it does give a positive result, that positive result is absolute convergence. And here at my endpoint, even the good endpoint where we do converge, the convergence is not absolute. And this is a conditionally convergent series. But this is the way I usually think of it. All right, so the numbers that give you the endpoints for your interval of convergence are always the numbers that make L equal to 1. And when L is equal to 1, the ratio test is inconclusive. All right, we do have to end it here. We're about 7 minutes over. I appreciate you guys hanging out a little bit late. There is a new homework dropping today that is just intro to power series stuff. There's going to be a handful of problems like this, and I want you guys to please work on that over the weekend. I know some of you have not yet taken the exam. I've got plans for a bunch of you to take them today. Those of you who took them on Wednesday, those will be graded for you by next Wednesday. Those who take them today, they'll be graded for you next Friday. If you need anything from me, remember you can reach out to me on Canvas, Discord, or email. That is it. All right. Take a deep breath and enjoy these power series.